Good day to you. So I'm taking a bit of a segue from my previous stuff, which was focused on graphs from R. I'm doing that because if I carried on, I think you'd all think I'm crazy for graphs. And I don't think the purpose that you use R is to make graphs. I think the purpose you use R is to do data science and perform analytical checks. It's about knowledge generation. It's not about making pretty pictures. So for that purpose, I'm taking a bit of a segue into hypothesis tests. Though hypothesis tests are their own rabbit hole and a very extensive piece of statistician field. They've got there's loads of them basically. And they're all fit for different purposes. And I'm in no way an expert of them. I might revisit the subject later. But what I wanted to convey to you is this idea that you're not just producing lots of graphs for the sake of graphs. You're producing graphs to find hypotheses. The idea being that you are looking for knowledge or information to get out of this database that you're analysing. And if you think about going back to your high school days, you understood about science, you did tests, and you produced a thesis and a hypothesis, and as you built up evidence, you became more and more sure whether that hypothesis was true or false. Well, data science is the same concept, except it's assumed that you've already got a big pile of data and information that's just sitting in a database and that's ready for you to access. So why not use that to analyze the hypothesis and problems that you're currently handling? So what I'm going to show you is the idea that we can work out if we've got two populations from a data set. We could have a data set that looks like this, but we could split that data up into two table sets, both of which we want to look at the IMDb value. And if you were to do that, you might end up with two very badly drawn data sets like this. But what I'm trying to show is if this green area was very large, you'd probably say whatever hypothesis you were following was wrong. But if it was very small, you'd probably say that the hypothesis that you were saying was true, that these two data sets are different. But it goes further. You can do this in, for probabilities and other things. Now, if you remember, we were looking at ggplot, and we were looking at some Kaggle data on Disney Plus, Hulu, Video Prime, and Netflix. And as you can sort of see, if we track those four different populations into a density graph, you get these sort of four overlapping values, but you can see they're different. So we might form a hypothesis test from this, a hypothesis that these four different entertainment packages are of different quality, that one might be better than the other because we've got our IMDb value at the bottom and we can see that they don't perfectly line up with each other. And you might pick two to compare with each other. Now, if you were focusing on the sheer number of graphs that we were producing previously, you'd have probably taken this graph, dropped it into an email to your customer or manager and sent it off and said, job done. But that's not enough, because really you haven't quantified how these things are different or why they're different. And even in fact, if they are different, because this could just be random noise. And whether this is significant or not matters. Whether this could have just happened randomly, that you could have, had a bunch of data and compared them and gone, well, I'm going to carry on with these hypotheses and be wrong. Now, the percentage for which you should look for is 5%. You should look to what we call a p-value. Is you should look to say, well, there's only 5% chance that result could have happened just randomly. It does create an interesting problem when you really think about it, because 5% is the PhD standard for most universities, which does mean that 5% of PhDs are, research is wrong, and 5% of published research is wrong, which means 5% of all science is wrong at any given time. But we have to keep on reiterating and gaining more data to carry on proving. And it's not enough just to say my hypothesis is I've got two different entertainment packages and one's better than the other. We do also have to state our null hypothesis. So it's not good enough for me to say, entertainment package A is better than entertainment package B. We have to decide whether what our null hypothesis is something like the opposite, that actually B is better than A, or is it that just there is no difference? And you can think of it like this. If I have an uneven coin, and I believe that it's biased towards heads. Now, if I say the null hypothesis is that it's biased towards tails instead, that's a fair null hypothesis, but the coin could be fair. And by having not clarified what your criteria for rejecting or accepting the hypothesis is, you don't allow yourself to communicate and analyze whether there is anything that out there which could contradict yourself. Now, I've rabbited on for a while, and what I need to now show you is some idea of how to do a hypothesis test in R. So what we're going to do, if I run a summary of the data, you can see I've got the min first quartile, median, mean, and third quartile max for IMDb. But it's not. So that would have been the makeup of the curvature of the previous one, where it was all kept together. Now I need to take that data and split it up into my two sets of information that I'm looking to analyze. So I use the filter, and I assign it to a new variable, which I'm going to call x. Remember this arrow value does the assignment. You're saying data, I'm looking at data key, and it has to equal Disney Plus. And y is Hulu. I've now got two values, x and y, and I have to decide what I'm actually testing now. So in my case with this, I'm not thinking that I think I'm trying to prove, is Disney a better entertainment package than Hulu? Now, the null hypothesis could be, no, Disney is not a better entertainment package than Hulu, but it's probably better wording if I actually say, that the two entertainment packages are of equal value as a starting point for my hypothesis, because I can run another test to conclude whether Hulu was actually better than Disney or, But if I'm not great at that wording, I might bring somebody some confusion. So then I can do a t-test. And the t-test in R will automatically work out it's a 2-sample t-test and pick the Welch hypothesis test. It will give me a p-value which is 0.731, which means if you see this is huge in this test. So looking at this graph, you could try and convince yourself that, and 731 is not 0.731, by the way, it's 73%, just so you're aware. And the p-value is a percentage that this just could have happened randomly. And if you see this, we would reject the hypothesis. We would not accept that Disney is better than Hulu. But if we'd worded it badly, we could have then gone, well, clearly Hulu is better than Disney. That's not what this is saying. This is saying that there isn't a big enough difference between these two values for us to conclude beyond random chance that one is better than the other. Because we can't conclude that one is better than the other outside of random chance, we shouldn't conclude anything. We should wait for more data. And this is where, if you'd have followed just making lots of graphs and sending them off to customers and managers, somebody could have made a major important decision without any comment or without any discussion on what was actually decided and what was meant. But if you do a hypothesis test, you can actually clarify the exact level of percentage of assurance that you think you're right. Now, there's degrees of freedoms, which I'm not hugely qualified to explain, and you have other information that's included here. But the really great thing about R is it's done this all for you. It's given you the p-value. Now, I really struggle to explain hypothesis tests and different variants without getting myself confused. I can give you the way to calculate this t-test is M being the mean, which you know how to calculate, U meaning the theoretical mean, divided by S being the standard deviation, divided by the square root of N, which is, as usual, the number of observations. And I can do that calculation, as I'm sure that you can, but it's quite difficult sometimes to know why that is if you're not a proper statistician. And what R takes out of this is you just get a function that you can put in the data and get a p-value really quickly. You can then talk about why that test was valuable, and as long as you've set up the test properly ahead of time, writing down a hypothesis and a null hypothesis, and you're clear what your two data sets are and what they mean, it's a good rule of thumb. It's a good place to start, and it's at least better than looking at one of these graphs. Now, I hope to return at some time with some more detail on different hypothesis tests and be less vague other than just let R calculate it for you. But honestly, in the first instance, it's probably best if you just let R calculate it for you because it makes it simple. So thanks for tuning in. Have a good day. Bye.